Hello, so welcome back. It is time for section 1.8. 1.8, you say, how did we get there, right? We're gonna do a little jumping around, right? So what have we done so far? So far, what are the first order ODEs we can solve, right? Now we're talking about solution methods, not just visualizing, right? So the first order ODEs we can solve are separable, which was in section 1.3, and linear, which was section 1.4. And really there's like a trifecta of the three big methods for first order ODEs. And the next one is exact differential equations for first order. So I'm gonna do these three guys in order, and we're going to skip around and go back and pick up some of the sections in between here at different parts of the course. Some you may even just do on your own for read and extra credit, we'll see. But this is one of the reasons why we're jumping to exact right now. So 1.8, here we go, okay? So let's just look at an ODE, okay? So let's consider the ODE. Consider the ODE, first order. Oops, only two dots there, but let's just look at this guy. Relatively innocuous looking, 2x plus y squared plus 2xy times y prime is equal to 0, okay? Alrighty, we're gonna just start with this particular example. So let's think about our methods that we have so far. Well, as we look at that, would you kind of say, would you think that's linear? You think that we're going to be able to solve that with our linear methods? Yeah, no, right? What's cluing you in right here? Well, this y squared, right? Y prime, well, if we divided by y, right, you might be like, oh, well, wait a minute, if we divide by y, right, then we'd be okay here, and we'd be okay here, but we'd have a 2x divided by y, right? That's not linear in y. That's a y to the -1, right? So, no, not linear, yeah? So this guy is not linear, okay? So that method is not gonna work. What about separable? Well, if we were gonna like try to go for separable, right, well then maybe we would get that stuff on the other side. So we'd have, you know, like 2xy, y prime is equal to minus 2x plus y squared, right? And then we would be like, well, what do we mean by y prime? Because we want to write it in different notation. So that means derivative of y with respect to x. X is our independent variable, y our dependent variable. And so we have that. Right, and then if we were shooting for separable, then we would have, we could divide this guy by, well, we want the y's on this side maybe and the x's on that side, right? So we'd have y dy is equal to minus 2x plus y squared dx divided by 2x, right? Okay, divide by 2x, leave the y's over there. And the problem would be, right, that guy right there, right? Okay, if that wasn't a y, then it'd be separable, but it is a y, so it's not separable, okay? Not separable. Okay, so we can't do either method, okay, that we've got so far. So these two guys don't work. Now what? It's not such a horrible looking differential equation, right? What does this equation say? Find me all functions out there in the world such that are y as a function of x, such that 2 times x plus the square of the function plus 2 times x times the function times its derivative ends up being 0, okay? I mean, depending on all of these different things, say that slightly differently, but they all mean the same thing. What are all the functions out there in the world that satisfy that equation with a derivative for an unknown function? Okay, so what do, right? It doesn't satisfy either of our other two guys. So we need something else. So one thing I am going to do is write it a little bit differently, okay? So got it written like this. We understand where this came from. We understand where this came from. We know we went for this because we were going for separable. But here's yet another way we could write this equation, okay? So we could write it as 2xy, I'm just going to change this guy up a little bit, 2xy dy, right, is equal to that thing dx, right? That's another way to write it, all the same, yeah? And we could bring that piece across if we wanted to kind of have this form to begin with, where we're setting something equal to 0, and so another way to write it is 2x plus y squared dx plus 2xy dy is equal to 0, okay? And maybe you could see that just directly from here, right? Replacing that guy with dy dx, right? And then writing it in a differential form. So this is a differential form, another differential form, because I've got it written in terms of differentials instead of derivatives, dy dx. Yeah? Okay, so these two guys are the same thing, right? This ODE, also known as this ODE, right? Well, why? Why is that a nice way to write that? Well, we're kind of stuck at this stage, right? Okay, so I'm just going to call this guy star. So I'm just going to, say we'll consider that. So I can just refer back to our little equation star, okay? And we really have nothing to do. We've got nothing. So when you got nothing, you just kind of like look for something, right? Okay, so here's our kind of, here's kind of the idea of an exact differential equation, of the solution of an exact differential equation. We've got no idea what the solution is. But, what if, we're gonna dream here. What if there was some function, we're gonna, from our solution of separable differential equations, we see that sometimes all we can do is write, some implicit relationship between y and x, right, as the solution. So we're not gonna get greedy and want a y equals some function of x like we have in 1.4 with linear differential equations, right, explicit solution that's guaranteed. So let's not get too greedy, but what if there was some way to implicitly write the solution? So what if there was some function, right, and we'll just call it capital F of x and y, that was some relationship between x and y, and we set that equal to 0, and that represented the solution of the differential, we set that equal to a constant, get a little carried away here, and that one equal to a constant represented the solution of the differential equation, okay? What if there was some function, capital F, depends on x and y, in that, we throw a bunch of stuff together, and some implicit relationship, and set that equal to a constant, and ends up being a solution of that equation, okay? An implicit solution. Okay, well, if that were the case, well, what could we say about this function? Well, anytime we see constants, one thing we like to do is what's easy to do with constants, take their derivative, right? So if that was the case, right, then we could, take the derivative of both sides. Oh, now here, what do we really mean? Well, if I think about this, y really depends on x, right? So this is implicitly a function of x. So if I would take the derivative with respect to x of both sides, right? Because that's my independent variable, so it's derivatives I like to take. This side's super easy, right? What's the derivative with respect to x of a constant? Very nice, 0, okay? So now our question becomes, well, what's the derivative with respect to x of this thing? Well, let's look at that here in just a sec, okay? And so really, let's just write this again, okay? So if I had some function f that was a solution of this differential equation, then then this would be a differential equation it would solve, right? Okay, so this differential equation and this solution. These guys go hand in hand. All right, now can we make a little more sense of this guy? We're gonna come back to this. No worries. Okay, form, not forms up. Okay, we're just gonna put this down here, and we're gonna come back to that. Yeah? Okay, so let's remember something. So what is this? This is what we want to know in question, right? What is this? Okay, what is this? Well, let's go over here. So let's recall in Calc 1, we learned the chain rule, right? Right? We learned the chain rule. So let's write it. How are we going to write that? Let's write it like this. The derivative with respect to x of, well, what was it? Derivative of composition, right? F of g of x. That's the way we learned it, right? Right? So the derivative with respect to x is some function f, right? Evaluated at g of x. Right? Okay. Well, what did the chain rule say? Well, you can either use Newton notation or Leibniz notation, and we're going to go with the longer one. It's the derivative of f with respect to g, right? The derivative of f with respect to g, right, or u, if you let u equal g of x, right, times the derivative of g with respect to x, right? F prime, evaluated at g, times g prime, same thing, right? Okay, g dx. Okay, so that's our chain rule, and we have this chain, right, where these guys link up and produce our derivative of this function with respect to x, how capital F changes as x changes, right? And that's kind of what we're saying here. Or sorry, lowercase f. Over here, capital F, how does capital F change as x change? It doesn't, right? Okay. We'll talk a little bit more about what that all means in a minute. But right now, let's just try to go through just the calculation of that derivative, okay? So you learn the chain rule in Calc 1, but as you go on in more calculus in Calc 3, you learn there's infinitely many chain rules, right? There's gazillions of chain rules, okay? So let's look at a more general chain rule. That might be scary for those of you who haven't taken Calc 3 yet. More generally, we can talk about any number of dependencies here and taking derivatives with respect to them. So more generally for us, what we care about here is the only one we're going to pay any attention to. So don't worry if you don't know all kinds of chain rules. We want to know about taking the derivative with respect to x of, instead of that, what are we doing? Well, we have really some function, I'll keep it as little f, just to try to keep this notation the same, but it depends on two variables, okay? So instead of, I just put in another guy there, right? Okay, so now f depends on two things, so if I'm going to take this derivative, the chain rule I want says, well, now this guy depends on two things, so I got to take a partial derivative of that. So the partial derivative of f with respect to the first guy, g, chain rule would say times the derivative of g is a function of a single variable. We're going to take this derivative with respect to x, so times the ordinary derivative of g with respect to x plus, right, what? Well, then we got to go to the next guy, right? The partial derivative of f with respect to, this time, good, h, times what? The ordinary derivative of h, with respect to x, yeah? Okay, so if we have that, then that's the chain rule that applies. So how does that connect up with this expression? So we're trying to take the derivative, the total derivative with respect to x of this function capital F. What does capital F depend on? X and y, right? But what do you know about y? Well, y is the dependent variable in a differential equation, And so y is really depending on x, right? Using x as the independent variable. So that's really what we have over there. That's really what that means. So if I'm going to take that derivative and use this chain rule, then what do I get? I'm going to get the partial derivative of capital F with respect to little x, right? Times the derivative with respect to x of that function, which is just x, right? Plus the partial derivative of capital F with respect to, good, y, partial f partial y, times the derivative of this function with respect to x, which is the ordinary derivative, dy dx. Yeah? All right, well, tell me about this right here. What is the derivative with respect to x of x? All right, 1. Very nice, right? Yeah? So, let's rewrite this guy. So what is this? So if I have derivative with respect to x of capital F of x and y is equal to 0, right? That's the same as our guy right down there. Or maybe I'll use black so that you can see better. Is partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx, where y prime of x is equal to 0. Okay, now maybe it's you're beginning to get some inkling of what we're doing. Remember our original equation, it had some stuff, right? Before we wrote it like this, it was some stuff plus some other stuff times y prime is equal to 0, right? Okay. So it's kind of like, hey, wait a minute. Well, if the stuff here and the stuff here are actually these partial derivatives of this particular function, then the solution of this differential equation would be given here as this implicit solution, that function equals a constant, right? That's kind of the whole point. Okay, well, let's try to write it in a differential form, kind of like this guy that would have it written. So if we wrote this in a differential form, instead of the derivative form, we would have partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy is equal to 0. So now we're beginning to get somewhere. You might not think we are, but we are. All right, so what's the deal, okay? As we look at this equation written this way and we compare it with this, the question becomes, right, well, is this expression the partial derivative of some unknown function with respect to x? And is this expression the partial derivative of that same unknown function with respect to y? And if so, we know the partial derivatives of this unknown function. And then we would just try to construct the function from those partial derivatives, set it equal to a constant, and we have our solution of this differential equation. So the question of whether these could possibly be such things is what exact equations begin to get at. All right, so let's write this in another way. So another way to write this in a different notation. That gets to be a lot of writing. So I think we already mentioned that sometimes when we're talking about partial derivatives, instead of writing out the big partial derivative notation, we just use the subscript notation. So this would be equivalent to writing f sub x. That means partial derivative of f with respect to x. That and that are the exact same thing, right? fx dx plus fy dy. Fy means partial derivative of f with respect to y, right? Fy is the partial derivative with respect to y of f, right? Fx is the partial derivative with respect to x of f, okay? So this is just shorter to write, and it spins off the tongue faster, right? Fx dx plus fy dy equals 0, yeah? Okay. All right, so we've got this whole idea, right? If we can justify that some differential equation, right, satisfies this idea, which we haven't really said so much exactly what that is, then this guy would be our solution to the differential equation. So our big question is, how do we say whether this thing multiplying the dx is really the partial derivative of some unknown function with respect to x? And how do we say that this thing multiplying the dy is really the partial derivative of that same unknown function with respect to y? If we had a way to know that, then we might call the equation something like exact. And then we would have a method for solving exact differential equations. What would that method be? How do you construct the f? Once you have the f, what's the solution? F of x and y equals a constant. You ready to tackle that here with this problem? And then we'll talk about it more in general. I think that might be the best way to go. Yeah. Yeah, let's do that. That way you see something explicit, okay? So, does fx, right, equal 2x plus y squared? If fx is equal to 2x plus y squared, right, and fy is equal to 2xy, then can we find a function, capital F, that will have these partial derivatives, okay? So, let's see what we could do. Let's just work with this guy for a sec, okay? Okay, so let's let fy equal 2xy, right? What does that mean? The partial derivative of f with respect to y is equal to 2xy, yes? How did you take that partial derivative? You pretended x was a constant, right? And took the derivative of f with respect to y. So if we want to try to figure out what f is, well, we can undo the derivative in the same kind of way that we would do with calculus. I would want to integrate with respect to y the partial derivative of f with respect to y, right? I'm going to integrate that with respect to y. Partial integration, right? If I integrate that guy with respect to y, then I'll get f of x and y. Yeah? So let's see what that would mean here. That would mean integrate with respect to y, 2xy. You're integrating with respect to y, just making sure you're clear on what you're doing, right? This helps you remember, oh, this is a partial integration. Pretending x is a constant. I'm integrating with respect to y, okay? So if I integrate that with respect to y, pretending x is a constant, then what would be my integral? Pretend x is a constant, the integral y squared over 2, right? And so what would I have? X, y squared, right? Add 1 to the exponent, divide by the new exponent, yes? Okay? I would get xy squared. Now normally what do we add? Plus a constant, right? But what else am I pretending is a constant? X, right? So I can't say plus a constant. I have to say plus some function of x. Let me just do g. It doesn't really matter. I'm trying to stay consistent with what I do. Yeah, I'll just say g. All right. So I did a partial integration, so what else I could get out is some function of x, right? So let's make sure that makes sense. You can always double check yourself. If I take the partial derivative of this with respect to y, what do I get? 10x is a constant, 2xy, that's what I said. What's the derivative of some function of x with respect to y? 0, partial derivative, right? Okay? And so here is an expression for f of x and y, which now has just this one unknown function in it, g of x. Yeah? Boy, it'd be great if we could figure out that g of x. Whoa, there's a little knee wobble. Okay, that little knee replacement isn't doing quite as well as I thought. So here we go. So it'd be great if we could find some way to figure out this unknown function g of x, right? Well, what could we do? We used this guy, right? We started with this guy. We integrate this guy with respect to y. We picked that randomly. It really didn't matter. But now what? We still have this guy that we haven't thought about. So we pick this one first, and then you integrate with respect to that variable. Then, well, that doesn't so good. Then you come back to this one, right? And then we can utilize this one in differentiating this guy. So our first step was to integrate. Our second step is to say, okay, well, here's my f. What if I now take the partial derivative of that function with respect to x, right? Whoops. Yeah, good. Where did I want my 2? That's also an fy, right? Here's where I want my 2. Try that again, okay? We used this guy. There's our 1, right? We used him, we integrated. Now what are we going to do? What we're going to do is say, okay, here's my function. I am going to now take the partial derivative with respect to x of this function and see what I get and see if I can match it up to this guy. So let's do that. What do we get? So when I differentiate this with respect to x, then I'm pretending what is a constant? Y, right? So what is the partial derivative of f with respect to x of x times y squared? Just y squared, right? Because it's x times a constant, right? That's what we think, right? Derivative of 5 times x is 5, right? Okay, y squared times x, y squared. Taking derivative with respect to x. And what is the derivative, right, plus? What is the derivative of g of x? Just g prime of x, right? Taking derivative with respect to x. So I use that guy, so now this is what partial f partial x would have to be, okay? And I look back and I'm like, okay, well this is what I want partial f partial x to be, right? So this must equal, if this guy is going to have this form, then this derivative I just took has to equal 2x plus y squared. Well, that's pretty exciting because what happens, right? If that's going to equal that, then I get y squared plus g prime of x equals 2x plus y squared. What happens? That says, I hope you can see this, g prime of x must be 2x, right? Okay? The y's canceled, right? The y's canceled. The y primes. And that's what I'm left with. And because I'm left with just a function of x, and g is a function of x, and its derivative is a function of x, since I just have a function of x, this is actually going to work. Yay, that's exciting, right? There really is such a function for which we're going to get that solution. And we're almost done determining it, right? Almost done determining it. So this unknown function g that was up here, that was the only thing left in our computation of our function capital F has this differential equation that governs it. And this is a nice, simple, regular calc, one differential equation where g prime of x is 2x. So what is g of x? You guys tell me. Good. X squared. Now, we could say x squared plus c, but we're not going to say plus c. Why? Or plus some other constant. Because what are we going to do once we find our f? We're going to set it equal to a constant. That's our solution. Okay? And so that will be all taken care of, plus a c1, and then we set that equal to another arbitrary constant. It's still an arbitrary constant, so we don't do that. Okay, so what do we then know? We found out what g of x is. We have these two guys, and so I'm going to just come up here and write, therefore, the capital F of x and y that goes along with this differential equation is x times y squared plus g of x. What did we say g of x is? X squared. Okay? We call this the potential. Talk about that in a minute. And then the solution, so the solution of our differential equation is what? Based on what we just talked about right there, so the solution of star is that this guy is equal to a constant, right? So I'll write it like this. What do we know? X times y squared plus x squared is equal to a constant. Yeah? That's our solution, given implicitly, right? You can't solve this guy for y without a plus or minus, right? Okay? You have to bring this across, divide by x, and if you solve for y, then you're going to have plus or minus. And then depending on which, if you get an initial condition, depending on where that initial condition is and whether y is positive or negative, you got to pick one of those two solutions, the plus or the minus, right? But not both. So we'll leave it in this form, implicit form, because it's more general, yeah? If you have a specific initial value problem to determine C, then depending on whether y is positive or negative, you could solve for things explicitly. There are several problems in your homework. You have to be careful about that, choosing the right solution. Okay, so this seems complicated, okay? So let's talk about this process. You surely, it's not. It's very systematic, okay? Very systematic. We surely don't want to have to go through all of this work that we just did, right? Where we try to write an equation, take a differential equation, the way it's given to us, write it like this: stuff times dx plus stuff times dy equals 0. Hope beyond hope that this is the partial derivative of some function with respect to x, and this is the partial derivative of some function with respect to y, and then go through the process of picking one of these guys to integrate. So we could have started with this one. You should do that for your own fun, right? Integrate this guy with respect to x first. You'll get an arbitrary function of y to add on. Then take the derivative with respect to y, set that equal to this, and then you should be able to come up with this exact same solution. So it doesn't matter which of these guys you pick. You got to integrate one of them with respect to the appropriate variable, take the derivative of your result with respect to the other variable, solve for the unknown function that comes from integration, and if you don't end up with something nice like this, if there were y's over here, then we would know, oh goodness, this didn't work. We can't do that. There is no such function. You don't want to go through all that work without knowing ahead of time it's gonna work, right? Okay? And so that's the big question that we have now, is how do we know ahead of time that it's gonna work? Okay? That's where we're heading. Okay, so you can read some of the physicsy stuff in your book if you like. These guys, potential functions, we also call them level curves, right? So if we think about f of x and y being some field, right, in an xy plane, then this is telling me a set of values for x and y where this function has the same constant, okay? Does that make sense? So let's see. Yeah. All right, let's jump over to how are we going to have a test to see whether this process will work, okay? That's our test for exactness that we're going to look for. So our general form is going to be, well, what? You know, so basically, we've got some function of x and y, so we'll call it m. That's pretty much standard. The generalization of this special equation, of this specific equation, some function of x and y times dx plus some other function, we'll call it n, of x and y times dy is equal to 0. Okay? So, this is a specific m and a specific n. Yeah? And we want to come up with a way, once we've put an equation in that form, to test these guys to decide if what we did over there is going to work. Because we don't want to do it if it's not going to work. Another way to think about this, right, is that, you know, you can think about the constant as the height in the z direction, right? So for each different constant, you're talking about what's the set of x and y values that produce a height of that value for this function, right? That's another reason it's called the level curves of f. Okay, so back to here. So let's do this same thing, right? What did we need? This is what we needed. We needed this guy m to be the partial derivative of f with respect to x, and we needed this guy n to be the partial derivative of f with respect to y. And we needed such a function to exist such that that was the case, right? Now, if you remember where this equation came from, it's fx dx plus fy dy, right? So you never forget what m is and what n is, right? M is just fx, yeah? So we want to test to see if there is some function, capital F of x and y, that has these derivatives. These partial derivatives. Okay? Where n would be. Can we come up with such a function? Okay? And that's what we're going to call exact. Okay? So, how do I want to introduce you to this? Okay. So this guy is exact. We want to test for exactness. If we can do this, then we have an exact equation. We want to test something that looks like this for exactness. Okay? Alrighty. So let's write down a theorem. You always love theorems, right? There's a theorem that says, let n, the partial derivative of m with respect to y, and the partial derivative of n with respect to x, and y and x, right? Let those all be continuous on some simply connected region. We'll just call it omega, okay? Omega, okay? One piece, no holes, okay? And it's region, so it's open, okay? So let them be continuous on some simply connected open region, omega, some region in the 2D xy plane, essentially, you can think of it as that. Then, what? Our guy, m of x and y, dx, plus n of x and y, dy, equals 0, is an exact, maybe you can't see that, I'll put it over here, is an exact differential equation, right? What? It's exact. It can be written like this, and therefore has this as a solution, okay? This is a total derivative of some function is equal to 0. Therefore, that function equal to a constant is the solution, right? So it's exact when we write it in this form. On that region. If and only if, right? This is a big word in math, right? Yeah, if and only if, what? My of x and y is equal to nx of x and y. Okay? So let's make sure we see where this is all coming from. We're not going to prove this theorem. It's actually a bit difficult to prove. Proving this direction is pretty hard. You need to take a upper level math class. Proving this direction is not so bad. It's basically the same construction that we just did with this example. We're going to do one more example, but just in generality with the m's and the n's. Okay? So what's really happening here? What has to be true? Now, what did we say m was? I'm going to switch to a different color. M was the partial derivative of f with respect to x, right? That's what m is, right? What is n? If the f exists, right? N is the partial derivative of f with respect to y, right? Now, you don't know f to begin with. All you know from a particular equation is stick it in this form and call this guy m and call this guy n. Whoever multiplies dx is m, and whoever multiplies dy is n, right? So, you can take the partial derivative. What is this? This is the partial derivative of m with respect to y, right? So what I look at this function and I take its partial with respect to y. And then I look at this function and I take its partial with respect to x. So the guy multiplying dx, I take the partial with respect to y, and the guy multiplying dy, I take the partial with respect to x. Whoops, that's an n. Yeah? And x and y. And then I look at those two things, and if they are equal, I'm guaranteed to have an exact differential equation, which means I'm guaranteed that the f actually does exist to make these things happen, which means I can go through that process and come up with the f, right? So what is this equation really, okay? So we need these guys to be continuous, so Whatever is multiplying here and here should be continuous functions of x and y, right? And then their derivatives should be continuous as well. M with respect to y, and with respect to x. So let's look at those guys a little more carefully. Let's notice that the partial derivative with respect to y of m, that's my, right? My is the partial derivative with respect to y of m, but that's the partial derivative with respect to y of, what is m? The partial derivative of f with respect to x. Yeah? What is that? That's the second partial of f with respect to y with respect to x. Yes? And now let's look at this guy. Maybe I'll do that in green. Okay, so maybe we'll come this direction. Nx means the partial derivative with respect to x of n. Yeah? But what is that? That's the partial derivative with respect to x of, what is n? Partial f partial y. That's not very good looking n, right? Right? Partial f partial y. So what is this guy? This is the second partial of f with respect to x. Yeah? If we use subscript notation, then this guy is f, we took the derivative with respect to y first, fy x, right? Took the derivative with respect to x second. We took the x derivative of fy, right? This guy is fy. So this is the same as partial x of fy, right? So this piece is fyx, yeah? In subscript notation. What did we do here, right? We took the partial derivative with respect to y of fx, right? So this is fx y, yeah? If you've had count 3, you know that as long as things are nice and continuous, right, then mixed partials are equal, okay? If we have continuity, then we have equality of mixed partials. That it doesn't matter what order you take those derivatives, right? That's one of the beautiful things in Calc 3, that if I want to think about these two guys, I can take those derivatives in either order, okay? And so that's our key to an exact differential equation, right? If the mixed partials of my function capital F are equal, then this guy is going to exist and solve this differential equation. And this equal to a constant is going to solve this differential equation. So let's do another example now that we kind of know what we're shooting for. Yeah? The proof is fun, but we won't do it because we don't have time. At least the one direction, at least this direction. Okay, so here's our test for exactness, right? This becomes our test for exactness. So let's think back to our other problem. The one that we did. Starting example. What was it? We wrote it as 2x plus y squared dx plus 2xy dy is equal to 0. So while we just blazed a trail straight ahead and dove right into partial integration and differentiation, we could, now that we kind of hopefully spent some time understanding why we would try to get to this and where it comes from and how it just arises in what is a kind of pretty cool way. We would look at this equation. We would say, okay, well, m is 2x plus y squared. It's the guy multiplying dx. Oh, remember, m is fx if this f exists, right? So I want to think about the mixed partial. What would fxy be? Well, that's my. What's my? It's 2y. Yeah? Okay? And then, right, this guy, okay, he's n is 2xy. He's multiplying dy, right? The guy multiplying dy is fy. Yeah? Okay, now I'm going to think about that mixed partial, fyx. Oh, so I'm going to take the derivative of n with respect to x, and if I take the derivative of n with respect to x, n partial x, and I treat y like a constant, and what is the partial derivative of 2xy with respect to x if I pretend y is a constant? Good, 2y, right? Because the y is like a constant, right? It's like the derivative of 10x, right? Think of y as 5 or something like that, right? Okay? So what did I discover? Lo and behold, right? My is equal to nx. And so indeed, these partial derivatives, mixed partials, are equivalent. And that makes this equation exact. And so we know that that process that we started with at the beginning of class is going to work, okay? I think maybe I'll stop this video and then just do another one where we just look at an example. Yeah? Sound good? Okay, just because I think it's getting a little long now. Okay, coming back for another example.